The journey of a steel drum begins with large steel coils that arrive at the factory. These coils are pre-treated and ready for processing. Specialized machinery unrolls the coils, feeding the steel sheets onto a conveyor belt. These lids are manufactured using a punch press, a specialized machine that delivers precision and speed. The process begins with a flat steel sheet carefully positioned between the punch, the upper part, and the die, the lower part of the machine. When the punch strikes, it forces the steel into the die, forming the lid's characteristic shape in just seconds. The design of the stamped lids includes several essential features. A raised outer edge, often called a bead or flange, ensures a secure fit with the drum body and provides additional structural strength. The lids may also feature embossed or recessed sections, allowing for compatibility with sealing mechanisms like gaskets or clamps. For open-head drums, these lids are designed to accommodate airtight seals to prevent leaks and protect the contents. This precision ensures that every lid forms a robust barrier, capable of withstanding pressure changes, handling rough transport, and maintaining the integrity of the drum's contents over its extended lifespan. The steel sections, now properly sized, are fed into rolling machines. These machines employ rollers that rotate in opposite directions while applying compression to the steel. As the sheet passes through, it gradually curves, forming the cylindrical shape characteristic of steel drum barrels. This rolling process is critical for creating the hollow body of the drum. Once the cylindrical body is formed, the open longitudinal ends of the sheet must be sealed. This is achieved through resistance welding, a process that uses heat and pressure to fuse the edges. The resulting seam is both strong and watertight, ensuring the integrity of the drum structure. Ripples, also known as corrugations or hoops, are formed along the body of steel drums to enhance their structural integrity and resistance to deformation. These ripples are created during the rolling process, where rollers compress the cylindrical steel body at specific intervals. The resulting ridges or hoops distribute stress more evenly across the drum's surface, preventing buckling under heavy loads or pressure changes. This design feature also improves handling, as the ripples provide added grip and stacking stability during transport. With the barrel body complete, attention turns to the lids and bases. These components are created using a machine known as a punch press. In this step, a section of the steel sheet is placed between the machine's upper punch and lower die. The punch strikes the steel, forcing it into the die and forming the desired shape. This process is remarkably fast, with each lid or base taking only seconds to produce. The lids and bases are then affixed to the cylindrical body. Each component is either manually or mechanically placed on the top or bottom of the barrel. A roller machine is used to flatten the edges of the lids and bases, creating secure seals called chimes around the barrel's rims. These chimes ensure that the drum is robust and leak-proof, ready to endure the rigors of industrial use. The assembled drum enters a specialized cleaning stage, where it is treated with a chemical solution designed to remove oil, grease, and other contaminants left from the manufacturing process. This solution, often a combination of degreasers and rust inhibitors, prepares the steel surface for subsequent treatments. This cleaning step is crucial, as any residue could compromise the drum's protective coatings or lead to premature corrosion. Once cleaned, the drums are transported to a drying room where they are exposed to controlled heat or high-velocity air. This ensures that no moisture remains on the surface, as even minimal residual water could interfere with the adhesion of paint and promote rusting. The drying room maintains a consistent temperature and humidity level, ensuring uniform results. The final stage is the automatic painting workshop, where drums are coated with protective paint, typically applied using spray systems for even coverage. Paint not only improves the drum's appearance, but also adds a layer of protection against rust and environmental damage. Automated systems ensure consistent application, optimizing efficiency while maintaining quality. The finished steel drum barrels are not only functional, but also highly durable, capable of withstanding years of use in demanding environments. Their robust construction and versatile design make them an ideal choice for storing and transporting liquids and semi-liquids across industries. Barrel making, or cooperage, is an age-old craft steeped in tradition, skill, and innovation. Barrels are integral to the production of fine bourbon, wine, and other spirits, playing a pivotal role in aging and flavor development. Bourbon barrels are a cornerstone of the spirit's identity, as U.S. law mandates that bourbon must be aged in new charred oak barrels. These barrels are typically crafted from American white oak, known for its durability and flavor-enhancing properties. Once the bourbon has been aged, usually between 4 to 8 years, the barrels have fulfilled their primary purpose in the bourbon-making process. Despite their limited use in bourbon production, these barrels have remarkable longevity. After their initial use, cooperages like the one described in Scotland give these barrels a new lease on life. Many of them are sold to distilleries and winemakers worldwide for aging other products such as Scotch whiskey, rum, and wine. Once the staves are bent and secured with metal hoops, the barrel undergoes charring or toasting. This critical step caramelizes the wood sugars, imparting complex flavors like vanilla, caramel, and spice to the spirits or wine aged within. A passionate industry, the cooperage industry thrives on passion and craftsmanship. While some cooperages cater to large-scale operations, others work closely with small artisanal winemakers, creating bespoke barrels tailored to specific flavor profiles. This diversity in clientele highlights the versatility of barrels and the personal touch cooperages bring to the craft. The barrels can endure several fillings, particularly in Scotch whiskey distilleries, where aging processes often span decades. A single barrel can potentially be reused for 40 to 50 years, given proper care and rejuvenation. The cooperage industry thrives on passion and craftsmanship. While some cooperages cater to large-scale operations, others work closely with small artisanal winemakers, creating bespoke barrels tailored to specific flavor profiles. The process begins with sourcing high-quality raw materials. Certified carbon steel is typically used as the primary material due to its strength and resilience. Suppliers must meet rigorous certification standards to guarantee the quality of the material. The selected steel undergoes several treatment processes to prepare it for production. These include cutting, forming, and welding to construct the tank's primary and secondary structures. For jacketed tanks, a double-walled design is created. The secondary tank is coated with thermoset resin reinforced with high-quality fiberglass, providing an interstitial space for leak monitoring. After manufacturing, the tanks are coated with synthetic industrial enamel, typically in blue. This layer provides protection against external corrosion and enhances the tank's lifespan. The production process is tailored to meet customer needs. Tanks can be compartmentalized or non-compartmentalized, with capacities ranging from 15,000 liters to 60,000 liters, or customized for special projects such as vertical or above-ground tanks. Waste generated during production is either recycled or treated to minimize environmental impact. These eco-conscious practices underscore the commitment to sustainability. The process begins at the scrapyard, where steel scrap is sorted, cleaned, and categorized based on its composition and quality. Sorted scrap is melted in an electric arc furnace. High temperatures generated by electric arcs efficiently liquefy the scrap. Alloying elements can be added during this stage to achieve the desired steel composition. During the melting process, impurities such as slag, a byproduct, are removed. The molten steel is transferred to a ladle where refining takes place. The refined molten steel is poured into a continuous casting machine, where it solidifies into semi-finished billets. These billets have uniform dimensions, ready for further processing. In the rolling mill, Billets are reheated and passed through finishing stands, where they are shaped into various final forms such as rods, bars, or sheets. The process ensures dimensional accuracy and surface finish. This streamlined process efficiently converts steel scrap into high-quality finished products, contributing to sustainability and industrial efficiency. Electric induction furnaces are widely used for melting scrap or sponge iron to produce steel ingots and billets. The process begins with feeding the raw material, primarily scrap or sponge iron, into the furnace. In India, especially in northern and western regions, scrap forms over 70% of the raw material. However, most induction furnace units use unprocessed or non-shredded scrap, leading to challenges such as low bulk density due to air pockets between scrap pieces. This results in inefficient power coupling, longer heat cycle times, and suboptimal furnace performance. These include segregating scrap based on type and quality, shredding it to remove rust and dust, and compressing it into dense pieces using a baling press. This processed scrap with higher bulk density enables faster charging, better power coupling, and reduced energy consumption. Efficient feeding methods like bucket feeding or vibro feeders further enhance productivity. Processed scrap offers numerous advantages, including a faster melt rate, reduced slag generation, extended furnace lining life, and reduced air pollution. For example, using 40% processed scrap in a 10-ton furnace can reduce heat cycle time by 10% and energy consumption by 5%, leading to significant savings. The production of steel bars through hot rolling is a highly organized and technical process designed to convert raw steel into durable, high-quality finished products. This process involves heating steel billets or ingots to a temperature that makes them malleable and passing them through a series of steps to achieve the desired size, shape, and surface quality. The first step in the hot rolling process is descaling, where surface impurities and oxide layers are removed from the heated steel ingot or billet. As steel is heated to high temperatures in a furnace, a layer of scale, oxidized metal, forms on the surface. This layer must be removed before further processing to ensure the final product's quality and structural integrity. Descaling is typically achieved using high-pressure water jets or mechanical methods, allowing for a clean surface to move into the next stage. After descaling, the steel is cut into manageable lengths known as billets. This step is often done using an oxidation cutting technique, where an oxy-fuel torch slices through the steel with precision. Once the billets are cut, they are transferred to a cooling pit. The cooling pit is a controlled environment where the billets are allowed to cool gradually to reduce thermal stress. This step ensures that the steel retains its mechanical properties and minimizes the risk of warping or cracking. Proper cooling is critical for maintaining consistency in the material's microstructure, which is essential for producing high-quality steel bars. After cooling, the billets are reheated in a push furnace. This type of furnace uses a continuous pushing mechanism to move the billets through a heated chamber. The purpose of reheating is to bring the steel back to a workable temperature, typically around 1,100 to 1,300 degrees Celsius. Once heated, the billets are passed through a reversible duo finisher rolling mill. This mill consists of two rotating rolls that compress the steel as it passes back and forth, gradually reducing its cross-sectional size and shaping it into bars. The reversible nature of the mill allows for multiple passes without needing to reposition the material, which improves precision and efficiency. The duo finisher ensures the steel achieves the desired dimensions and a uniform finish. After the rolling process, the steel bars are cut to the required lengths using a high-speed cutting saw. This step is critical for meeting customer specifications and preparing the bars for shipment. The cutting saw provides precise, clean cuts, ensuring uniformity in the final product. By the end of this stage, the steel bars have reached their final shape and size, but additional finishing steps may still be required. The final stage in the process is straightening. After cutting, the steel bars may exhibit minor bends or distortions due to the stresses experienced during rolling and cooling. A bar straightener corrects these imperfections by applying controlled mechanical force, ensuring that the bars are perfectly straight and meet the required tolerances. This step is essential for maintaining product quality, particularly for applications where straightness is a critical factor. The hot rolling process for producing steel bars is a sophisticated sequence of operations designed to transform raw steel into reliable, high-performance products. Each step, from descaling to bar straightening, plays a vital role in achieving the desired quality and specifications. The process begins with hot-rolled coil steel, which forms the raw material for the pipe piles. Each steel coil is inspected thoroughly for tensile properties and yield strength to ensure that only the highest quality materials are used. Atlas technicians test the coils during the initial stage to maintain flexibility and quality control. After inspection, the coils are slit into precise widths based on the diameter of the piles to be produced. The slit steel is then loaded onto the production line. As the steel is uncoiled and flattened, it is joined end-to-end using a butt weld, forming a continuous sheet for uninterrupted production. Importantly, the butt weld sections are cut out and discarded, ensuring that they do not compromise the integrity of the final product. Once uncoiled, the continuous sheet of steel enters the forming stage, where it begins to take the shape of a pipe. 5 forming rolls, resembling rolling pins, gradually curve the flat steel sheet into a U-shape. Each roll deepens the curve incrementally until approximately 70% of the pipe's final shape is achieved. At this stage, the process allows for quick adjustments to produce piles of varying diameters and steel gauges, meeting the specific needs of customers. The rollers, which are polished continuously during operation, contribute to the precision and speed of this phase. The U-shaped steel strip proceeds to the welding stage, where the edges are joined using the electric resistance welding (ERW) technique. This method employs 2 copper contact shoes to pass an electrical current through the edges of the steel strip. The resistance to the electrical flow generates heat, raising the temperature in the weld zone to approximately 2,700 degrees Fahrenheit. Following the welding process, the pipe moves to the final preparation stage. Here, the welded pipe undergoes cooling with a constant stream of water and coolant to prevent cracking or splitting. The pipe is then sized precisely using tools like Turk's heads, which refine the surface finish and dimensions. The final step in preparation involves cutting the pipe to the required length. A rail-mounted cutoff saw travels alongside the pipe, enabling precise cuts without disrupting production. The ability to produce pipes of nearly any length, up to 125 feet, gives Atlas the flexibility to meet a wide range of project requirements. The production of Atlas straight seam electric resistance welded ERW steel pipe piles is a process designed to deliver high-quality structural supports for deep foundation projects. Quality assurance is integral to the manufacturing process, ensuring the reliability and durability of each pipe pile. After welding, the pipe undergoes ultrasonic testing, which detects internal flaws in the weld and confirms its structural integrity. Any defective sections are automatically removed to uphold Atlas's 100% quality guarantee. Destructive testing further verifies the product's performance. The cone test uses a hydraulic press to expand the pipe until it fails or achieves a predetermined expansion without compromising the weld. The flatness test assesses the ductility of the steel by flattening a sample at different angles to the force.